Hello everyone, and welcome back to our CompTIA Cybersecurity Analyst course. Today, we're diving deep into a topic that is at the very heart of what a security analyst does. Chapter 5, Analyzing Indicators of Compromise. We often shorten this to just IOCs. Think of yourselves as digital detectives. In the world of cybersecurity, attackers almost always leave behind clues, digital fingerprints, footprints, the stray fibers of their intrusion. These clues are your IOCs. Understanding how to analyze these IOCs is absolutely critical. As a cybersecurity analyst, your primary role is to act as a guardian of your organization's digital assets. You are on the front lines, tasked with detecting, investigating, and responding to threats. IOCs are the signals that alert you to a potential problem. They are the breadcrumbs that lead you from an initial, often subtle, sign of trouble to the full scope of a security incident. Without the ability to effectively analyze them, an analyst would be flying blind, unable to distinguish normal activity from a malicious intrusion. The skills you'll learn in this chapter will empower you to move from a reactive to a proactive security stance. Instead of just waiting for an automated alert, you will learn to actively hunt for threats by looking at raw data and spotting the patterns that indicate a compromise, long before a major breach causes damage. To ensure we get the most out of our time today, let's clearly outline our two main goals. By the end of this lecture, you will be able to, first, explain the common techniques used to investigate indicators of compromise. And second, you'll be able to categorize the different types of tools used for IOC analysis. It's not enough to know the techniques. You also need to know which tools to use for the job. We'll move logically from the what and why of IOCs to the how of investigating them. First covering the techniques and then diving into the specific tools. Let's get started. All right, let's begin our deep dive into investigative techniques. One of the most common tasks for an analyst is diagnosing potential malware. When you find a suspicious file, your first question is this legitimate or is it something malicious? The fastest way to get an initial answer is by using message digests or hashing. A hash is a unique digital fingerprint of a file created by a mathematical algorithm. Even a tiny change to the file will result in a completely different hash value, making it a powerful identification tool. As an analyst, you calculate the file's hash and compare that value against online malware databases. If your hash matches an entry, you get instant confirmation that it's a known piece of malware. This saves massive amounts of time, as the security community has already done the heavy lifting of analyzing it. Here in Figure 5-1, you can see examples of different hash types like MD5, SHA-1, and SHA-256 that can be generated from a single file. But what if the hash doesn't match anything? This is when the real investigation begins. You need to perform a deeper analysis using one of two primary methods: dynamic analysis or static analysis. Dynamic analysis is the behavioral approach. You run the suspicious program in a safe, isolated environment, like a virtual machine, and observe what it does. You monitor the OS commands it issues and watch its effects on the system in real time. What files does it create? What network connections does it make? Static analysis is the opposite. You do not run the program. Instead, you perform a digital autopsy, decomposing the file's contents while it's at rest. You examine its file structure, recognize patterns in embedded text strings, and look for clues within the code itself. In static analysis, we often have to deal with packed or obfuscated files. Attackers hide their code, so a key step is to decompose the file to reveal its true contents and structure. This involves examining things like the program's interactions, which you can see in Figure 5-2. We also look at the file's structure, like the imported functions in Figure 5-3, which tell us what the program is capable of. And as shown in Figure 5-4, we recognize patterns in readable text strings, which can reveal hard-coded commands or URLs. A more advanced static analysis technique is identifying dynamic command and control URLs created by what are called domain generation algorithms, or DGAs. This is where the malware algorithmically creates a list of potential C and C, command and control, servers to contact, making it much harder to block. Now, let's shift techniques to another huge source of IOCs, email. To analyze email effectively, you need a foundational overview of how it works. Your client, the mail user agent or MUA, sends a message to a mail transfer agent or MTA, which acts like a digital post office, routing the message to its destination. Every server that handles the message adds a stamp to the email's header. As you can see in Figure 5-5, by reading these headers from the bottom up, we can trace an email's true path and spot forgeries. This analysis is crucial for detecting common threats like phishing, malware delivery via attachments, spear phishing, and various social engineering scams. To combat these threats, we rely on three key defense mechanisms. Sender Policy Framework, or SPF, verifies that the email came from an authorized IP address. Domain Keys Identified Mail, or DKIM, adds a digital signature to verify the content hasn't been tampered with. And finally, DMARC tells receiving servers what to do if SPF or DKIM checks fail, allowing a domain owner to enforce a reject policy on fraudulent emails. Our final technique involves analyzing the most unpredictable element: people. User Behavior Analysis, or UBA, focuses on establishing a baseline of normal activity for each user and then detecting significant deviations. This has evolved into UEBA, which includes entities like servers and applications. UEBA is excellent at spotting abnormal account activity. For example, an employee who always works 9 to 5 suddenly logging in at 2 a.m., or an accountant who has no business in the engineering department suddenly trying to access the source code repository. These are major red flags. A classic example is impossible travel. If a user logs in from New York and then 5 minutes later logs in from Moscow, the system knows this is physically impossible. It's a high confidence indicator that the account has been compromised. However, UBA has its challenges. It requires a long time to build a good baseline, and it can generate a high number of false positives from legitimate but unusual user behavior, which can lead to alert fatigue for analysts. All right, let's move on to the tools that power these techniques. For file analysis, the most important tool is the sandbox. A sandbox is a secure, isolated environment where you can safely execute a malicious file without risk to your network. There are two main types. A local sandbox is typically a virtual machine you manage yourself, offering maximum privacy. A remote online sandbox is a web-based service where you upload a file and receive an automated analysis report, which is fast and convenient. For local analysis, you'd use specific utilities. Redshot takes snapshots of the Windows registry to see what changes a program makes. SSDT view helps you find low-level system hooks used by rootkits, and driver view lists all loaded drivers, helping you spot suspicious or unsigned ones. When it comes to remote sandboxes, the most famous is VirusTotal. As you can see in Figure 5-8, you submit a file and it scans it with over 70 antivirus engines, giving you a quick, crowdsourced verdict on whether the file is known to be malicious. For a much deeper dive, there's Joe Sandbox. Figure 5-9 shows its comprehensive report, which includes everything from process behavior and decrypted network traffic to screenshots and even a full video of the analysis run. It's designed for deep dive investigations. Finally, for those who need a private, in-house solution, there's Cuckoo Sandbox. As seen in Figure 5-10, it's a powerful, open-source platform that provides automated analysis reports, giving you the power of a remote sandbox with the privacy of a local one. Next, let's look at network analysis tools. The undisputed king here is Wireshark, a protocol analyzer. As shown in Figure 5-11, it captures every single packet on the network and dissects it, allowing you to see the raw conversations between devices. It's essential for troubleshooting and security investigations. It's important to differentiate protocol analysis from flow analysis. While Wireshark gives you the full packet content, flow analysis, shown in Figure 5-13, provides a metadata summary: who talked to whom, for how long, and how much data was sent. Flow analysis is less detailed, but because the data volume is so much smaller, it's ideal for establishing long-term network behavior baselines and quickly hunting for anomalies across the entire enterprise. Reputation tools act as a background check for your IOCs. Tools like Whois, shown in Figure 5-14, give you domain registration data, while Abuse IPDB provides a crowdsourced reputation score for IP addresses, telling you if they're known for spamming or hacking. Finally, we have large-scale log correlation platforms. The primary challenge they solve is log management, collecting, parsing, and normalizing the millions of events generated across thousands of devices into one searchable format. This category is dominated by three platform types: a SIEM, or Security Information and Event Management Platform, is the central hub for log aggregation and alerting, as seen in this dashboard. A SOAR platform, shown here, orchestrates and automates responses to those alerts. And an EDR, or Endpoint Detection and Response, provides deep visibility and threat containment directly on endpoints like laptops and servers. As we bring our lecture to a close, let's quickly summarize the main topics we've covered. We explored the core techniques for investigating IOCs, breaking them down into three key areas: diagnosing malware, analyzing suspicious emails, and interpreting user behavior. We then surveyed the analyst's arsenal, categorizing the tools of the trade. We covered file analysis tools like sandboxes, network analysis tools like Wireshark, reputation tools for context, and the major log analysis platforms like SIEM or SIEM, SOAR or SOAR, and EDR. By covering these topics, we have met our two-chapter objectives. You should now be able to explain the common techniques for investigating IOCs and categorize the primary tools used in those investigations. This knowledge is a critical foundation for your career. The work of a cybersecurity analyst is a continuous cycle of vigilance and learning. The skills you've begun to build today are in high demand and are essential for protecting our digital world. Stay curious, keep asking questions, and never stop hunting for the truth hidden within the data. Thank you for your time and attention. I look forward to seeing you all in our next class. Have a great day.